Welcome to This Explainer. Today, we're making the jump from just writing code that technically works to architecting software that truly lasts. You know that sinking feeling when you tweak one tiny line of code and somehow completely bring down the entire application? Yeah, we've all been there. It is a terrible feeling. So today, we're going to fix that by mastering the absolute fundamental building block of software design, the method. Here is our cognitive roadmap to conquering software architecture together. We'll start with the art of the method, tackle our two structural pillars, cohesion and coupling, dive into refactoring and code smells, lock down our blueprints with specifications, and finally look at a really fascinating case study called the equals trap. Let's get right into it. Section 1. The art of the method, the building blocks of our code. Think of a method as a single room in your software's floor plan. It's an independent module encapsulating a highly specific computational task. It's how we take massive, incredibly complex problems and break them down into manageable, isolated pieces. Now, in a messy, highly coupled system, what we lovingly call spaghetti code, every piece relies intimately on every other piece. It's literally like a house where knocking down a single interior wall accidentally collapses the entire roof. But modularity allows us to carefully separate our concerns. This structural isolation is what makes our code reusable, readable, and sustainable over the long haul. The real magic happens when we treat a well-designed method as a black box. You feed data in, you get computation out. This is a powerful concept called procedural abstraction. We want to completely hide all those messy implementation details, the underlying algorithms, the internal variables, behind cleanly designed parameters. Think about a sorting method, for example. As the caller, you frankly don't need to know if it's using quicksort or merge sort behind the scenes, right? You just hand over a messy, unsorted list and trust that black box to hand back a perfectly organized one. You don't need to know the inner workings, you just need to trust the contract. Moving right along to Section 2, cohesion, keeping it together. If our method is a room, cohesion is basically checking if the furniture inside actually goes together. It measures how related the code instructions are within a single module. We've got a spectrum here, counting down from the absolute worst to the absolute best. At the very bottom, coincidental cohesion. This is a nightmare, just a random grab bag of unrelated code thrown together for convenience. Moving up, we see temporal cohesion, where tasks are bundled just because they execute at the same time, like initializing random variables. Getting better, we hit communicational cohesion, where tasks at least share a theme and operate on the exact same dataset. But functional cohesion right at the top, that is our holy grail. That means your method performs one single, unified, highly focused task and absolutely nothing else. That is the targeted interior design we're aiming for. Which brings us to Section 3, coupling, the dependency trap. Now, if cohesion is the room itself, coupling is the hallway connecting those rooms. It describes how much one module depends on another. Obviously, rooms need doors, so some coupling is required, but bad coupling makes your software incredibly rigid. Look at these two extremes. On the left, content coupling. This is like having a terrible roommate who rummages through your things, one module reaching right into the inner workings of another. It creates this fragile ripple effect where one tiny change breaks everything else. But on the right, data coupling. This is exactly where we want to be. Modules share information cleanly and safely through predictable parameters. Total module independence is maintained, and our perfect black box metaphor stays completely intact. All right, Section 4, refactoring and code smells, the renovation process. Look, even the absolute best blueprints get messy once construction actually starts. We apply quick patches, rush to meet aggressive deadlines, and suddenly our beautiful modules start to deteriorate. Professionals use the term code smell to describe surface-level warming signs in the code base. It's a funny question, I know, but if your code smells, it's usually pointing to a much deeper architectural rot. It immediately tells us that our cohesion might be dropping or our coupling is getting way too tight. Let's check out a few of the usual suspects. Are you using public or global variables? Massive red flag. They create unwanted coupling and make debugging a total nightmare because literally anyone can change the state at any time. What about deeply nested loops? That usually means your method is trying to juggle way too many tasks, totally wrecking that functional cohesion we just talked about. Long parameter lists and data-only classes are also huge warning signs. And my personal favorite, overly extensive comments. If you have to write an entire paragraph just to explain a single block of code, the underlying code is way too messy. If you're seeing any of these signs, you've got to stop adding new features and start refactoring. Next up, Section 5. Specifications, the ultimate contract. So how do we actually guarantee our black boxes do what we want? Specifications. These are our literal blueprints and binding technical contracts. A precise specification gives implementers exactly the information they need and absolutely nothing more. It all comes down to preconditions and postconditions. Think of it like operating heavy industrial machinery. The precondition is your safety check. Are the guards in place? Is the power stable? If the caller skips that safety check, the machine, or your method, makes absolutely zero promises about what happens when they pull the lever. The environment has to be mathematically correct before execution. This side-by-side perfectly demonstrates why just writing things out in plain English is so risky. Saying a method searches an array sounds totally fine, right? Until that array happens to be null or memory efficiency really matters. We assume context as humans that computers just don't have. By swapping informal language on the left for formal, mathematically backed pre- and post conditions on the right, we eliminate that ambiguity entirely. We state exactly what must be true going in and exactly what state is guaranteed coming out. No guesswork allowed. Let's apply this. Section 6, Case Study, the equals trap. To really ground this theory, let's look at a trap hiding right in plain sight. Java's root equals method. This method actually implements a strict mathematical equivalence relation based on 3 critical rules. Number 1, it's reflexive. X equals X must always be true. Number 2, symmetric. If X equals Y, Y must equal X. And 3, transitive. If X equals Y and Y equals Z, then X inevitably equals Z. If you override an equals method in a subclass and ignore these strict rules, you will completely break your ops reliability. Data structures like hash maps literally relied on these mathematical guarantees. Mess it up, and you might drop a crucial object into a collection and literally never be able to retrieve it again because the collection mathematically doesn't recognize it exists.
And it gets trickier. If you subclass an object and try comparing it to its parent, you risk violating a massive tenet of object-oriented design, the Liskov substitution principle. Basically, a child class should seamlessly stand in for its parent without breaking logical correctness. Let's say you have a parent point object on a grid and a child color point that adds color. If the parent thinks it equals the child because they share the exact same coordinates, but the child disagrees because the parent has no color to match against, boom, you've just destroyed the symmetry rule. Overriding methods isn't just matching syntax. It is about strictly honoring a mathematical contract. You simply cannot arbitrarily change the preconditions mid-game.
Ultimately, anybody can string together code that happens to compile and execute today. You can link highly coupled, low-cohesion methods, rely on vague natural language, and just ignore the obvious code smells. But the system you build will be incredibly fragile. So I want to leave you with this critical question. When your code base inevitably gets reopened 3 years from now, is the next developer going to find a fragile house of cards or a sustainable, masterfully engineered blueprint? Aim for functional cohesion, demand loose data coupling, and rigorously honor your specifications. That's how you stop just writing code and start architecting solutions that actually endure. Thanks for joining me for this explainer.